So far in this chapter, we've studied just a variety of different factors that can influence the rate of SN2, SN1, E2, and E1 reactions. And we know the faster reaction wins, right? So that's why rates are important. That can help us predict what our products are going to be and what the mechanism is going to be. Now, unfortunately, these factors don't pull in the same direction. So predicting the outcome of the competition between an SN2, SN1, E2, and E1, it's just not always going to be clear cut. And so we have 4 steps that offer a way to kind of systematically evaluate each of the factors we've examined so far so that we can pretty reasonably predict the major products. So we are going to examine these 4 steps over the next few slides using equation 935 as you see here. So the very kind of first thing you want to do is you want to determine whether an SN2, SN1, E2 competition is feasible. And so to do this, you need to evaluate, let me put up here, you need to evaluate several things. One of the things is you need to ask yourself, do you have a suitable leaving group? Okay. And so we need to come here and we need to identify what our leaving group is. And so to identify what our leaving group is, we need to be able to identify our substrate. And so when we look at our substrate is here. It's S2-chloropentane. We see that the leaving group would be a chlorine here, right? Because that's the only thing that's really different than carbons and hydrogens. So that chlorine has to be our leaving group. And when it leaves, it's going to leave as chlorine minus. And so when we evaluate our leaving group, right, we need to kind of remember these 2 points, which I'm showing here in purple. The leaving group should be at least as stable as F minus, right? And I want you to, where I'm getting that information from is figure 911 on one of the previous screencasts that we did where we had that good, poor, unsuitable. And so that leaving group has to be at least as stable as fluorine minus. Well, just kind of quickly here, we can look at this and we can say, okay, fluorine minus is really small. Chlorine minus is going to be bigger. It's going to accommodate that negative charge better. So it's going to be a suitable leaving group. I just want to remind you here that unsuitable leaving groups are things like alcohols, ethers, amines, hydrides, and just an R minus, which would be like a carbon group minus. Now, we can do some things to help these, like add an acid, but those would be your unsuitable leaving groups. Then the next thing we need to do is we need to evaluate the type of carbon. So if we're going to evaluate, do you have a suitable leaving group? The next thing we really need to evaluate is the type of carbon, right? To make sure that this is feasible. The type of carbon that we're looking for here is it sp3 hybridized? And so when we talk about the type of carbon, it's the type of carbon the leaving group is bonded to. Okay, and so I'm going to do this in blue here. The carbon that we're evaluating is this carbon right here. Okay, and we look at that carbon right there and we see there are no double or triple bonds. There's no charge. So we know that carbon has 4 bonds. And because that carbon has 4 bonds, we know that carbon is sp3 hybridized. Okay, so that's one of the things that we like to do. The other thing that I really like to do here is I like to go ahead and figure out if that is a secondary, tertiary, primary carbon. And so I look at this and I realize that's a secondary carbon. It's just something that I like to do in this step. Your book is going to do it later. But while I'm looking at that carbon, I feel like it's just easier to do that. Then what we need to do, 3, is evaluate the attacking species. Okay, and by evaluate the attacking species, what we're really doing here is just identifying if there's a recognizable attacking species. And so when we look at this, this is our attacking species. Right? But it's the entire species. It's not like exactly one of the things it's going to attack. So what we need to do is we need to identify if there's a spectator ion there. And so we come in here and we can say, okay, hey, look, that sodium there, that's a spectator ion. And so that's not going to attack. So our true attacking species here is bromine minus. And so we've identified that we do have attacking species here as bromine minus. And so we do expect an SN2, SN1, E2, or E1 competition. Okay, so we've kind of asked ourselves 3 questions here in step 1 to figure out if this is feasible. And yes, the correct answer, well, the answer here is one of these 4 reactions is feasible. So the next step is going to be to rule out the reactions that are completely unfeasible. Now, when we look at this and we're looking at reactions that are unfeasible, I want you to remember kind of these points here that I've written for you under step 2, rule out reactions that are unfeasible. We are going to rule out an SN2 reaction if the substrate is tertiary, since tertiary substrates cause excessive steric hindrance, right? So I'm just going to put here because of sterics. Well, let's not be lazy. Let's say steric hindrance. Okay, so what we're trying to do here, all right, is we say, look, if that's a tertiary carbon, we have 4 reactions we're trying to decide between, right? We have an SN2, we've got an SN1, we have an E1 and an E2. Which of these can we completely rule out? Okay, if we can rule out an SN1 and an E1 if the heterolysis products aren't sufficiently stabilized. And so that's the case when you have a substrate that's primary, unless the resulting carbocation is resonance stabled, right? And so when we talk about those things that are resonance stabled, what you're looking for there are those allyl cations where you have a double bond, or the benzyl cations where you've got resonance, okay? We're also kind of looking here to, right, if the solvent is aprotic, right? And so examples of aprotic solvents, which are really common, are acetone, DMSO, right? Or DMF. Okay. Those are the really common solvents. So we can rule out an SN1 or an E1 if we have an aprotic solvent. And then kind of that third thing here, I'm going to just draw a line so that we know that all these are going with that second bullet point, is if the leaving group is poor. And we have 2 poor leaving groups, that's F minus or RCO2 minus. So we can rule out an SN1 or an E1 if it's a primary or methyl carbon. The exceptions, of course, are that allyl cation or benzyl cation, if the solvent's aprotic, and if the leaving group is poor. And then we can rule out an E2 or an E1 if there are no beta hydrogens. Now, I want to remind you, right, that when we talk about beta hydrogens, this would be like the alpha carbon here. and the beta hydrogens would be on either side there. Okay, so the alpha carbon is found where there's that leaving group. So let's go through and ask these questions here in step 2 for this reaction. So we look at this. It's a secondary carbon, right? So we know it's a secondary carbon. So we can't rule out SN2. The leaving group is not poor. The leaving group is chlorine, so it's not poor. We can't rule out SN1 or E1 based on the because it's a secondary, it's not primary or methyl. But we can rule out an SN1 and an E1 because of DMSO here. So because we have an aprotic solvent, we rule out SN1 and E1 reactions. So SN1 is gone and E1 is gone. So now we're trying to decide between SN2 and E2. And we have beta hydrogens, right? So we can't rule out E1 or E2. So the only thing we can really rule out here is the SN1 and the E1 reactions. So we're going to go to step 3 next, and we're going to determine whether the remaining reactions are favored by the attacking species. So let's see. We've got SN2 and E2. Okay, so we've narrowed it down to these two. This is either going to be an SN2 or an E2. And so here is step 3. Now, these are all the things that you need to evaluate each time, okay? Now, just like before, we're going to evaluate these, we're going to talk about these, and then use this equation 935 as an example. So SN2 is favored by a strong nucleophile. SN1 is favored by a weak nucleophile or by a low concentration of a strong nucleophile. E2 is favored by a strong base, and E1 is favored by a weak base or a low concentration of a strong base. So what we're really doing here is we're really focusing in on the attacking species. Okay, so step 3 is all about the attacking species. And for our example here, the attacking species is bromine minus. So we need to ask ourselves some questions about bromine minus. So the first thing we need to ask ourselves is it a strong or weak nucleophile? Well, right there, it has a negative charge. So because it has a negative charge, it's a strong nucleophile, okay? And that's it. If it's got a negative charge, it's a strong nucleophile. If it doesn't have a negative charge, it's a weak nucleophile. Now, we need to figure out, is Br minus a base? Okay, is it a strong, well, it's a base, but is it a strong base or a weak base? Now, you can memorize the table of strong bases and weak bases if you want, but you see, I'm lazy. I don't want to do that. So I think about, hey, what type of, this is the base, right? So what acid did this come from? This came from HBr, okay? And I know, because I memorized my 7 strong acids in general chemistry, that HBr is a strong acid. And I know strong acids have to have weak bases. So Br minus, sitting right here, is a weak base. So when we look at this, we say, okay, look, I have a strong nucleophile and a weak base. And the only 2 reactions that I can choose from are SN2 and E2. So SN2 is favored by a strong nucleophile. SN1 is favored by a weak nucleophile or a low concentration of a strong nucleophile. Well, we've already ruled out SN1, right? And then E2 is favored by a strong base. E1 is favored by a weak base. Well, we've already ruled out E1. So what we can do here is rule out an E2, because see, E2 here is all we've got left, and it's favored by a strong base. So I'm going to make that a blue dot. So I come up here and I say, okay, hey, look, I got a weak base, so it can't be an E2 reaction. So that means most likely this reaction is going to proceed by an SN2 mechanism, right? And so a lot of this kind of deciding what is ruling out the things it can't be. But to be able to do this, you have to be able to identify, do you have a good leaving group? Do you have a strong base or a weak base? Do you have a strong nucleophile or a weak nucleophile? If you don't know how to do that, you are in trouble here, folks. So make sure you know really well how to go through and do this. Now, sometimes at this stage, you are not going to have a cut and dry example. Sometimes you're going to have to apply a tiebreaker, right? Because you'll just have an SN1 and an E1 reaction or an SN2 and E2. So let's talk about the tiebreaker. Okay, so a tiebreaker for an SN1 and an E1 reaction. So if you're left at this step and you only have an SN1 and an E1 reaction, you need to determine and really think about heat, okay? Where if heat is applied, then it's an E1 reaction. And then if there's no heat, right? So remember, when heat is added, it's going to say specifically heat. It's going to have a temperature like 100 degrees Celsius that's higher, right? So not like 45 degrees Celsius, but 100 degrees Celsius, or a delta that shows that heat's being applied. Well, as you clearly heard, there was a ring of the doorbell, and so if there's a little pause there and then we're picking it back up, that's why you have not missed anything. Okay, so we've talked about the tiebreaker for SN1 and E1 reactions, but let's talk about the tiebreaker if you just have SN2 or E2 reactions left. You need to determine whether the attacking species acts better as a base than a nucleophile. And the best way to kind of do that is that the attacking species is going to act better as a base, and it's going to favor E2 over SN2 if it's bulky, right? Otherwise, both SN2 and E2 remain favored. And so we could actually get a mix of products. So basically you just kind of, here bulky is your word here that you need to look at. And so that's just kind of something that's the end. So you may not narrow it down to one, it may be two, right? And we may get a mix of products. Now, on the next slide, what we're going to see is a summary of these 4 steps that we've talked about. And so if you're a visual learner, this can kind of be really, really helpful for you. And so, like, for example, you can see here, and we did this on each slide. We start out with these 4 reactions, and then here's our step 2, cross out reactions that can be rolled out. SN1 and E1, and the reason is because they were aprotic solvents. And then step 3, circle and keep reactions that are favored by the attacking species. Well, SN2 was favored, right? Because it was a strong nucleophile, but it was also a weak base. So a weak base favors E1. And so we could say, hey, look, it's probably not going to be E2, it's going to be SN2. Then we can apply tiebreakers, and there was no tiebreaker that was necessary because the SN2 was the only thing that was left. So that's our winner here. Now, a lot of times what you'll be asked to do is you'll be asked to predict what's the winner, but then immediately asked to predict the major product, right? Because, okay, we can predict what the winner is, but we also need to predict the major product. And so we'll have to show the mechanism. So when we look here, this is the mechanism for the SN2 conversion of the alkyl chloride to an alkyl bromide. The electrons come in here and they attack this chlorine here. So we draw an arrow here and it bumps the chlorine off. And that's a backside attack. Now it's an SN2, and we remember from our SN2 reactions that this is going to form the opposite enantiomer. So we started out with R, and now we're going to have the opposite enantiomer. So we cannot forget stereochemistry. Do not forget that. So that a lot of times would be the end of the example. So let's look at our second example here. right? And I'm gonna, we're gonna look at this guy, right? So this is the example we're really working with here. So I had to, again, pause the screencast for just a moment. So if it broke up, you didn't miss anything. So this is the reaction we're looking at. And they already have kind of all the answers here, but I wanted to walk through this with you. So we're going to systematically consider the factors, again, outlines in steps 1 through 4 that we talked about on the previous slide. So here for step 1, we are going to identify what our substrate leaving species is. And that's this bromine here, right? And so we know that bromine is a suitable leaving group. We also know that bromine is attached to an sp3 carbon, okay? So that carbon right there, that is sp3, okay? Now, I like to go ahead and identify if that carbon that's sp3 is primary, secondary, tertiary, etc. And I look at that, and there are 3 R groups that are attached to it, and of course the bromine. And so that tells us that is a tertiary carbon, right? So we've looked at that. So we've looked at our substrate. Now we need to evaluate our attacking species. And it may look suspiciously like we don't have an attacking species here, but we do have an attacking species. This is our attacking species right here. Now it is under the arrow, but it's a suitable attacking species. It has that alcohol group. Remember, when we have an alcohol group, we do have electrons on the alcohol. Now, this is also the solvent. Okay. And when a reaction where the solvent's also the attacking species, that's called solvolysis. And so that lysis just means kind of to break. Okay. And you're going to see that all the way through science. You're going to lyse cells. They're going to break apart. But basically this is just where the solvent's responsible for that lysis or bond breaking. Okay. So the solvent's acting as the attacking species here. That's solvolysis. So we know that we have a feasible reaction. So we're going to go to step 2. And so when we look at step 2, we can immediately rule out an SN2 because we have a tertiary substrate. So that's what all that means is we're going to have some excessive steric hindrance. Right? So we have an excessive steric hindrance. The backside attack cannot happen. We've crossed out the SN2. Now, for step 3, we are going to really focus in on that attacking species, which is CH3OH. And when we look at this, CH3OH, that's an alcohol, but what we notice is there's no negative charge. And so we say, hey, look, that's a weak nucleophile, okay? And so a weak nucleophile favors SN1 over SN2. So weak nucleophile SN1. It is also, CH3OH is also a weak base, right? When we look at the conjugate acid of that, the conjugate acid is CH3OH2, right? And any alcohol that's protonated is just a super weak acid. Any alcohol that's protonated like this is a stronger acid. So it leaves us generally with a super weak base. And the reason it's a stronger acid is because it really wants to give up that proton to get rid of the positive charge. So it's going to release that proton really quickly. So that gives us a super, super duper weak base here. So we can kind of put all alcohols here into the weak base category. And so because it's a weak base, it's going to favor E1 over E2. So we can keep both SN1 and E1 reactions then. So now we have the tiebreaker. We have to come in and apply the tiebreaker. And so we're going to apply the tiebreaker for SN1 and E1 reactions. The tiebreaker for this situation comes down to really whether heat is added. If we look back up here, there's that symbol. Let me choose a different color. There's that symbol delta, right? And we know that delta means heat. And so in this situation, heat favors the E1 reaction, elimination over substitution, because of that increased entropy, right? And so we end up with our winner here, which is E1, okay? Now, you also need to be able to do the mechanism for this. And so when we look here and we do the mechanism, I'm going to come right on down here, right? You would need to say, okay, this occurs by an E1 mechanism, and I'm going to show this E1 mechanism. And so I know the first step is heterolysis, where this bond is going to break. So those electrons are going to go up to be on that bromine, right? So that first step is heterolysis. Okay. And you end up with that tertiary carbocation. Now, this is where you have to come in and draw in this H here, right? So that we can steal a beta hydrogen for the elimination to occur. And so we're going to come in, we're going to steal that proton, that beta proton, and those electrons then are going to fall down here and form a double bond and now satisfy the octet for that bottom carbon, so that we now have 4 bonds. And so this is an elimination. And now we have that major product right there. So that's 3-ethylpent-2-ene. So make sure that you know not only which mechanism is happening here, but also that you can predict the mechanism and predict that final product. I've done this here because I want you to see it. It's also written here for you as well. If you want to see it in the book, it's in 938. Let's do another example. Right? Oh, before we do another example, I do want to mention that we are going to have a minor product. So notice here that this is our major product. We come over here, even though we considered heat to break the tie between substitution and elimination, it's really important to understand that heat is a minor factor. And so it's not going to dramatically influence the relative amount of products. So we would also expect a minor product. Now, this is why you really need to look at questions, because a lot of times the questions will say, predict the major product of the reaction. And so you don't have to show the minor product. But when we do synthesis in the laboratory, right, anything we're learning in class, we need to walk into the laboratory and understand. In the laboratory, we would end up getting a minor product. And so we would have to work on a separation method to separate out our minor product from our major product. And that can be something like distillation. It could be using extraction, right? So there's a lot of different ways that we can do this. If you took instrumental analysis, HPLC is a really great separations method. So we would separate these products out. But on most of the problems that you're going to see, it's going to ask you just for the major product. Let's do another kind of thing here. So we are looking here at this problem, okay? We have a kind of this circular molecule here, and we need to identify the leaving group. Remember that tosylates here are really good leaving groups. So we've got an O- and that tosylate, and that's really our leaving group. And so that is very stable. It's a very suitable leaving group. The next thing we need to do is look at the carbon that's attached to. The carbon that's attached to does not have any charges. It doesn't have any double bonds or triple bonds. And so we know that is an sp3 carbon. We can also look at this and see that it is a secondary carbon. Always like to go ahead and do that here. Okay. Now, what is our attacking species? We're going to come in here and remove that sodium so that the attacking species is CH3 CO minus. Okay. Now, this is a tert butoxide anion. Right? So it's a T-butyl anion. It's called a T-butyl because off of the carbon, right, we end up with CH3, 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 and then the O. So it looks like that. And so the idea is that kind of looks like a T, okay? And that's why it's called tert butyl or T-butyl. So that's just something to kind of be aware of. Well, come on. There we go. All right. So that's our attacking species. And so it's got a negative charge on it. It's a great attacking species. And so we would expect that this reaction would occur. Okay. So we've done step 1. So for step 2, we need to start asking ourselves if there's anything we can rule out. We notice that we have DMF, right, as our solvent. So the solvent here is DMF. It is aprotic, right? And so that means we can rule out SN1 and E1. Those are not going to happen because we have that aprotic solvent. We can't really rule anything else out. It's secondary. If it was, so we have to consider SN2 and E2, right? So we need to move on to step 3. So in step 3, we're really going to focus on the attacking species. And so that attacking species is CH3 CO minus, okay? It's got a negative charge. So because it has a negative charge, it is a strong nucleophile, okay? And then we need to ask ourselves, is this going to be a strong base? It is a strong base because it is stronger than the OH minus. So this means the attacking species is going to favor both SN2 and E2 because we have a strong nucleophile and a strong base, and those favor SN2 and E2 respectively. So we're left with these two as candidates. So we need to apply the tiebreaker between an SN2 and an E2. And so this is where sterics really come in. I drew this base for you, and this T-butyl group particularly is very bulky. So the attacking species is very bulky. Anytime you see a T-butyl group, that's going to be a really bulky species. So it will act better as a base than a nucleophile. There's really too much steric hindrance for it to undergo the backside attack of a substitution reaction. And so because it's a bulky base, E2 here, which is shown here, is the winner, right? And so this is a way that we can systematically look and figure out how to undergo and choose what our product's going to be. Now, to determine the major E2 product, let's look at the mechanism really quickly. Okay, so it's here. Notice in the substrate that there is an H atom on each carbon here and here next to the carbon that tosylate group is attached to. Okay, and so it may appear that there are 2 possible E2 products depending on which proton you remove. But this is a stereospecific reaction, which means it's going to favor the anticoplanar conformation of the substrate. So this is stereospecific, and it favors the anticoplanar conformation of the substrate. Okay, so what's going to happen here is that it's more likely that that H is kind of on the opposite side of the leaving group. And so it's going to attack this H here. That's what anticoplanar means. It's just on the opposite side. And so it's going to come in, it's going to attack that H. Those electrons are going to come down here and form a double bond, and it's going to bump off that tosylate group. And it's going to give us this major product here. Now, we're still going to get a minor product because some of this can be removed. But again, remember, most of the time you're going to be asked, what's the major product of the reaction, not what's the minor product per se. Let's do another example. Okay. Draw the complete mechanism and predict the products for the reaction shown here, right? And so we have our bromo methyl D1 benzene. Now, I want to talk about the D here. This D is deuterium, okay? So the D that we're shown here is deuterium. And that's what we call heavy hydrogen. It's hydrogen with 2 neutrons instead of 1 neutron. And it shows up differently in some spectroscopy. And so it helps us figure out some of these mechanisms, specifically when and what protons are removed, right? And so that's really helpful for us. But deuterium is a little heavier than hydrogen, but it acts the same way as hydrogen, with the exception of in different spectra. So we're going to draw the mechanism and predict the products for this reaction. Okay. So we've got this, it's dissolved in methanol. And so the very first thing, before we can draw the mechanism, we have to choose what mechanism we're going to draw, okay? And so we need to ask ourselves, is there a suitable leaving group on an sp3 hybridized carbon? And so we need to identify the leaving group. So I'm going to come in here and I'm going to say, okay, hey, look, that's my leaving group. That leaving group is Br minus, right? That leaving group, we've talked about so much. It's more stable than, it's going to be more stable than fluorine. So it's a very suitable leaving group. It's also on an sp3 carbon, right? So we also know, looking at this, that this carbon is secondary, okay? Now we need to look at the attacking species. So when we come in here, our attacking species is CH3OH. We know that's going to be a suitable attacking species. It's also the solvent, so this would be an example of that solvolysis, right? So because we have a suitable attacking species, and we have a suitable substrate with a leaving group, we know that SN2, SN1, E2, and E1 reactions can occur. So, right, we go to that's step 1. So now we go to step 2, right? And we're here, SN2, SN1, E2, E1. We're trying to rule these out. And it says, what reactions can we rule out on the basis of the type of the substrate, solvent, leaving group ability, or the absence of beta hydrogens? So when we look at this, right, and I have made a mistake. I said that was a secondary, just super excited because I did not pay attention to that deuterium. That deuterium acts as hydrogen, so we actually have a primary. Oop, right there. Okay, so what reactions can we rule out on the basis of the type of substrate, solvent, leaving group ability, or the absence of beta hydrogens? So the substrate there is primary, right, which normally leads to a excessively unstable carbocation, and we would rule out an SN1 and E1. However, notice that this is benzylic. It's got that big old benzene group next to it, which gives it some stabilization. So the substrate here is benzylic, and so that resulting carbocation is resonance stabled. So we're not going to rule out those reactions. Now, we do look at this and realize there are no beta hydrogens. So this is our alpha carbon. We look next door and there's not a beta hydrogen here. So there's no way that an E2 or E1 reaction can happen because there's no beta hydrogen to be removed. So no beta hydrogens. And so because of this, we can rule out these E reactions. So it's going to go through a substitution reaction. So the next question we ask ourselves, we're gonna come into the attacking species. Is it a strong or weak nucleophile? So we have CH3OH, right? It's uncharged, so there's no charge, so it's going to be a weak nucleophile. And then it's also going to be a weak base. Because remember, CH3OH2 plus as an acid is a very strong acid, right? Because it's a protonated alcohol. It's got that charge, so it's going to be really strong. So this would favor, right? When we look at this, the base, when we talk about bases, that really is E2 and E1, but we've already rolled those out. But when we talk about a weak nucleophile is going to favor an SN1 over an SN2. So, right, the winner here is SN1. We don't have to apply a tiebreaker. We're going to say, look, this is an SN1 reaction. But that's just part of this process. Now we have to draw the complete mechanism and predict the products. So we're going to come in here. We have carbon, got some stereochemistry here, and deuterium, and bromine. Okay, and we know the first step here is going to be heterolysis. This little guy here is going to pop off. Okay, and we're going to see this carbon, a deuterium, a hydrogen, and then, right, this carbocation, okay? Now, these electrons are going to come in and they're going to attack that carbocation, okay, in a substitution reaction. And what we're then going to see Yep. Sorry, I have made a mistake here with we lose our stereochemistry there because we go we sit planar now, so we don't have any stereochemistry. Okay, and so we have this, and then immediately we're going to go through a proton transfer. Okay, where these electrons are going to come and grab that proton, and those electrons go there. And then we end up with that is our product. So I hope that kind of the myriad of examples we've done, this is really just, this whole screencast has really just been how do we choose, and then some mechanism practice. So I hope the myriad of problems that we did helps, but know that this is going to be our activity for our in-class activity, because really this whole chapter and the information you learn is all applied in trying to figure out, is it an SN1, SN2, and so on. So if you're still kind of stuck on that and the reasoning behind it, don't worry. We will work on this more in class.